All right, now we're recording. Okay, so recap. Last time we talked about the visualization of retain viz, and then the model agnostic approaches, Shapley value and Lime, and then we talked about representation learning, how you can learn representations of not only the patients but also the diagnosis codes. So we've seen some examples applying Word2Vec on electronic health records. And today will be the extension of that using domain knowledge. So domain knowledge, it's here in this medical terms, domain knowledge would refer to anything that is curated by medical experts. So examples could be diagnosis code hierarchy. SNOMED CT, we'll talk about that in a brief moment. And then GRAM is the probably one of the very first method that tries to incorporate neural networks with domain knowledge, which is also one of my papers, but that was like also some time ago. I think it was presented in 2017 KDD, so that's also now pretty an old paper by AI standards. But it was like probably the first paper to do that, actually, because that was back in the day. All right, then we'll briefly talk about knowledge graph, how you can view electronic health records as knowledge graph, and then present two papers very briefly, because it would be kind of, maybe it's an advanced topic, so it's not for today's material. So we'll cover very briefly about two papers, MIME and graph convolution transformer. All right, so before we get in, right, yeah. Maybe we should talk about diagnosis. No, I think I have an example of that. All right, so GRAM was one of my another projects between when I was a PhD student and Sutter Health that I did like 2 internships at. So the objective is to tackle 2 challenges. One is data insufficiency and the other is interpretation. So data insufficiency meaning that so far, I guess Mimic is not a very big data set, but when I was introducing RNN to try to predict heart failure, I was using about like 33,000 patient records or something. So 33,000 sequences are a pretty sizable volume, but it's not always the case. You have like thousands of patient records. I mean, like if you ask the question like what is the minimum amount of patient records to properly train RNN, it's a debatable question. I would say 10,000 with 10,000 sequences, you can still like get by. You can still properly train RNN to see some. I think like 10,000 patient records is probably not a bad number to see RNN outperform logistic regression. So it's not that bad. And even with Mimic 3, where I think there are only like 7,500 patients, maybe like 8,000 patients who made at least 2 visits. So like forming a sequence. So 8,000 patient records is also, it's trainable. I mean, it won't be too ridiculous to use RNN on 8,000 patient records. But it's not always the case. You have like thousands and thousands of records. So as said here, only large organizations have easy access to large data sets. So like national level hospitals like Asan Medical Center or Seoul University Medical Center. Is that right? Seoul National University Hospital. Yeah, Seoul-daeyeon. Like national level university hospitals or medical centers like that, they have like tons of data, probably millions of patient records, but local hospitals, not so much. So it's not always the case that you have like thousands of patient records in your hand. And in the case of rare diseases, even if you're a national level hospital, you don't have thousands of occurrences of that specific rare disease because it's called rare disease for a reason. So yeah, so data insufficiency challenges arise in multiple locations. So that is one of the objectives of this paper. The other is interpretation. So you want the learned representations, the diagnosis representations or medication representations like that. Like you want the learned representations to align well with established medical knowledge. So when I say established medical knowledge, like domain knowledge, obviously. And we want the model to be somewhat explainable to what it's doing underneath, like under the hood. So like, I mean, interpretation itself is a very loose term. People say their model is interpretable in various like dimensions. Like some people use attention and say that their model is interpretable. Some like like as far as attention goes, retain is probably one of the most interpretable models. But some are playing like fast and loose with the definition of interpretation. But anyway, so in this case, in GRAM, in this case, we are referring to at least providing some insight into what's going on under the hood of the engine that is machine learning. I mean, that is neural network. So two challenges, two objectives. One, data insufficiency, and the other is interpretation. Oh, by the way, I forgot to mention, was there any question related to previous topic, the interpretability from the last lectures? Any question? It doesn't have to be interpretation. Like anything related to the course, no? All right, okay. Sometimes I wonder if nobody asks question because it's the course itself is so perfect, like everybody's understanding everything so far, or is this just that nobody really cares? It's really hard to understand. All right, I guess there is no question, so I'll just move on. All right, so as I said, two challenges, and the solution that we propose in this paper is to use medical ontologies. So like domain knowledge is a very broad term. So medical ontology is a more concrete definition. So what I mean by medical ontology is something that could be represented as a directed acyclic graph, DAG, in short. So a lot of knowledge in medical domain can be represented as a hierarchical, like clinical constructs. So for example, ICD-9 code, International Classification of Disease, ICD-9 codes can be seen as a DAG, having a DAG structure, like this. So this is a subset. I mean, of course, this is not the entire tree of ICD-9. So I just took a subsample. I just took a subset of the tree to show as an example. So on the very top there is a root node, of course, because it's a tree, and root node would be an uninformative node. It's just some disease, like it's a disease, and then right beneath root there are, I think there were like 17 or maybe 16 high-level categories, and I took 3 of them here as an example. So neoplasms it's a concept that has, like anything that has to do with cancer falls underneath this term, neoplasm. Anything that has anything to do with like infectious disease or parasitic diseases, it would fall under this. And anything that has to do with your mind, mental illness, would fall under this. So if you unfold neoplasms, then there are probably a lot more than this, but three of the subcategory of neoplasms is cancer of lymphatic hematopoietic-ish tissue. Probably I forgot the English version, like 백혈병. I forgot what you call 백혈병 in English. Leukemia. Yeah, leukemia is probably okay. Leukemia is here, right? So leukemia falls under this benign neoplasm. So that would be like the good cancer. So, what is that? 양성 양성종양. Yeah, 양성종양. So benign neoplasm would be 양성종양. Cancer of skin. So anything to do with your like skin cancer, like 피부암. So, and also if you unfold the benign neoplasm, then I think we're moving on to different body parts. One is benign neoplasm of uterus. The other is, I mean, of course, there will be more than these two, but I'm just showing two here. So maybe we should move on to the actual examples in the website. All right, give me just a second. Oh, we have more participants. All right, let me just see who's here so that I don't forget to do the attendance. All right, give me like 5 minutes. All right. Okay. So we have 3, 4, 5, 6, 16, 18. Okay. All right, that's cool. All right, then moving on to the ICD-9 website. All right, everybody seeing the website? I think they should. All right. All right, so yeah, we were unfold. So as I said, I think there are about 20 different, like very high level categories, and then we were unfolding neoplasms. So neoplasms, and then there are 1, 2, 3, 4, like, I don't know, 10, 11 like subcategories of a neoplasm. We were unfolding benign neoplasms, and then, wow, okay, so I would say 20, 25. So like all different parts of body parts, like ovary, eye, kidney, genital organs, brain, thyroid glands, all that. So I think we were about to unfold, give me just a second, unfold unspecified benign neoplasms. So unspecified, where is that? Other and unspecified. Okay, no. Wait, wait, what? That's weird. Oh, I think this is the one. Yeah, okay. Benign neoplasm of other unspecified size. Right, this, so under this, there are neoplasms of colon. Wait, that is kind of weird. Okay, maybe the example I was showing in the PowerPoint, I think that was a wrong example. I think it should be, okay, yeah, probably I did something really weird. Colon, is there colon? So there is no colon here. I kind of don't get it. Oh, okay, I see. No, I don't. All right, okay, so sorry about the confusion, but I think I incorrectly drew the example in the PowerPoint slides, but you get the idea. So you move on to like different body parts, and then once you select a specific body part, let's say you select ovary, and then in the I think inside, okay, 220. So 220 is probably the lowest, like the leaf node in the tree, but some other trees like neoplasm of skin, okay, there are more than just neoplasm of skin. So there are like different types of neoplasm of skin. So neoplasms of skin of lip, neoplasms of eyelid. I didn't notice, didn't realize there could be neoplasm on your eyelid. That's new. All right, I don't know, 1, 2, 3, 4, yeah, 9 different, like 9 subcategories of like cancer. I think we were coming down. We jumped into like maybe 5 different layers now. So 216.0 is the leaf node. So usually it's 5-digit IC9 codes, but in this case, it's only 4-digit. So, and if you click this, there's nothing more. So this is the leaf node. All right, so that was the quick tour to IC97. Oh, maybe while we are here, while we are in the website, let's try to search for SNOMED CT. Right, SNOMED CT. So SNOMED is another example of domain knowledge, which is way bigger than ICD-9 code hierarchy. So SNOMED is a very comprehensive ontology. Can I see an example here? Oh, okay, here's a browser. That's cool. Unfortunately, SNOMED is there is a trade-off. So SNOMED is a very comprehensive. It's like a humongous ontology. And when I say ontology, it's because there are more than just one relationship. So previously in ICD-9 code, there was only one relationship between different nodes, which is like parent-child relationship. So like neoplasm of ovary is the parent of the neoplasm of skin is the parent of neoplasm of skin of lip, or neoplasm on your eyelid. So that would be the child, and the neoplasm of skin would be the parent. So there's only one like arrow or one edge in that ontology, or in that DAG structure, which is parent-child relationship. But in SNOMED, all right, so SNOMED, there are way more relationship than just parent-child relationship. I think there is like the reason of, or body site of. Let me see. So maybe I can just search for something. Leukemia. Leukemia? All right, leukemia. All right, so when you click leukemia, okay, when you find leukemia, so obviously there is parent-child relationship. So I guess leukemia is the parent of these two things. No, I'm sorry. These two things, malignant hematopoietic neoplasm and malignant neoplasm primary, they are the parents of leukemia. So obviously there can be more than one parent. There can be 2 parents. So it's no longer a tree now. Let's see. What else do we have here? Maybe we should click this. This should be more interesting. Like, okay, so now, I mean, that's the reason why SNOMED CT is kind of more difficult to use compared to ICD-9 code. I mean, of course, there's no comparison in terms of volume, but it's because it's a big ontology. It's really hard to like find the right type of information that you're looking for when you're using SNOMED. So obviously there was leukemia. There's also leukemia. There's leukemia cutis. There's acute leukemia. There are all kinds of different variations of leukemia. So yeah, and each node provides different information. So now that I've clicked this one, chronic leukemia, now this has both parent and children. So there's this parent-children relationship, but there's other relationships such as finding site. So finding site means where this particular disease occurs in your body part, and it says that the finding site of chronic leukemia is bone marrow structure, so which would be your 골수 in Korean. And associated morphology, I don't know what that is. So yeah, anyway, so as I said, there are more than just parent-child relationship when it comes to, I mean, when you're looking for information in SNOMED. So and of course there is parent-child relationship as well. So it's more comprehensive. It's like the superset of ICD-9 code, and it has way more number of nodes in SNOMED compared to ICD-9 taxonomy. So ICD-9, I think there are about 10,000 different, like 10,000 unique disease codes, but in SNOMED there are at least 100,000 different nodes, maybe million. I'm not really sure. I've never really properly used SNOMED. It's really, because as I said, it's kind of like computationally difficult to properly and efficiently use SNOMED. But if somebody can come up with a way to like manage or exploit SNOMED properly, that would be great. Yeah. All right. So yeah, those were two examples. Maybe we could go a bit more, like tour a bit more into the domain types of different types of domain knowledge. I think there is something called drug network. Maybe not. It's not this type of medication drug network that I'm looking for. NDC. All right, so national drug code. So this is another like different types of domain knowledge. So if you are using, so when you guys were pre-processing Mimic 3, the prescriptions table, I think there were different types of drug names. All right, so yeah, in the prescription table, in the previous assignment number 2, we were using drug only, but there are different like ways to represent each drugs or each medication. One is GSN, the other is NDC. So GSN is, I think this is, I forgot what okay, forget about that. And GSN is one of the ways to represent a drug. NDC is probably one of the most popular ways to represent a drug. So NDC is National Drug Codes. And as you can see here, it consists of about 10 or 11 digits. And the first 4 digit represents the labeler, which is the company that labeled this drug. And then the next 4 digit represents the product code, so the code that is used by the specific company. And then the last 2 or 3 digits, I think, yeah, the number of digits could vary. Like maybe this could be 3, this could be 3 or 4, this could be also be 3 or 4, something like that. And then the last part of the digits represents the package code. So you can break it down into like different subsegments. So this again kind of like works as a domain knowledge. If you are interested in using certain for example, like these 4 digits represent Prozac cash capsules 20 milligram, and then this was like total 100. So like so 100 capsules of Prozac. So like a single capsule would be 20 milligram, and then this package, this product that you see in the pharmacy would have like in the box there would be 100 of them, 100 capsules, and it was manufactured by this specific like pharmaceutical company. Could be Pfizer, it could be maybe it could be Yuhan Yang. No, probably not, because this is American number. This is American code system, NDC. So it could be Pfizer, it could be Gilead, it could be like Novartis, all the different kind of pharmaceutical companies. Yeah, so like when you have this kind of code, you can like maybe if you're not interested in the company, you can throw the first 4 digits away. Or if you're interested only in the company, then maybe you can take only the first 4 digits, something like that. You can like incorporate this kind of domain knowledge into your classifier. All right, so let's end our tour through the different types of domain knowledge. All right, back to the medical ontology. Right. So sorry about the incorrect depiction of the subset of ICD-9 hierarchy. But anyway, you get the idea. Like you start from the top when it is like the most uninformative, and you reach to the bottom, the leaf node, which are typically 5-digit ICD-9 codes that you see in the actual raw data, like any EHR. All right, so moving on. So the reason that we are so just to back up, so there were two challenges that we want to solve here. So one is data insufficiency, the other is interpretation, and the proposed solution was to rely on medical ontologies that is typically represented as a directed acyclic graph, and then we've just seen a lot of different bunch of like DAG structures. Right. So this is a subset example. Right. The reason that we propose to rely on medical ontologies is, first of all, it's a reliable source of information because it's constructed by the experts in the field. So it's like the actual doctors who got together to like label all kinds of different diseases and then structure them in a very particular way. I mean, of course, ICD-9 codes was constructed for billing purposes. So if anybody remembers, in the very first maybe or second class of this course, we talked about how the reimbursement process works. So a patient goes to the hospital, gets treated, and then because the patient is insured, the patient pays only like the very small portion of the entire like fee, and then afterwards the doctor will like file a report to either the insurance company or to the government to get the remaining sum, the remaining portion of the fee that he or she is supposed to receive. So that's the reimbursement process, and that when the doctor is filing a report or like writing the report, what kind of services that he or she provided to the patient, that is when you use the ICD-9 codes. So the ICD-9 codes were created for billing purposes. So let's see. So the doctor would say like, this patient had these kind of symptoms, and I performed these kind of services. Like for like this particular ICD-9 code is like $500, and this particular ICD-9 code, like leukemia, could like, I don't know, like millions of dollars in United States because it's crazy there. And like, I don't know, like fever could be some particular 5-digit ICD-9 code, and that's like some dollars. Like every single ICD-9 code will have like a corresponding like fee attached to it, and then the doctor will fill the reimbursement report with ICD-9 codes and then send that to the government or the insurance company, and then the insurance company or the government will evaluate the report, the reimbursement application, and then like pay the like the correct amount of money to the doctor. So that is why ICD-9 codes were developed. So it's not to treat the patient, it's for getting paid. So there are certain like discrepancies between how like machine learning researchers view ICD-9 and how doctors view ICD-9. So ICD-9 disease codes the codes don't necessarily accurately represent the status of the patient because it was developed for billing purposes. So you should like, it's a kind of the thing that healthcare researchers care about, like why certain codes were developed or why certain information was recorded in the EHR to begin with, and why you shouldn't rely on certain types of information in the EHR as a machine learning researcher, because like they were recorded for some other reason and you want to use that information for another reason, like something like that. Like you should always care about the discrepancies. Anyway, so but still ICD-9 codes are pretty accurate because, I mean, as far as like billing codes go, it's a super accurate construction because it was constructed by medical experts. So it's better than nothing still. And another reason that we propose to use medical ontologies is because concepts close to one another are likely to be associated with similar patients. So what I mean by this is that like knowledge could be transferred between nodes or disease codes that are located in the vicinity, in the neighborhood. So as an example, we'll go back to the subset. So for example, let's say this particular IC9 code this particular disease is a very rare disease. So you don't see that very often in the real life. But maybe this does. Maybe this is a very common one. This is a very, very rare one. And well, I mean, there wouldn't be many opportunities that you learn to represent well this particular rare disease, but you'll have tons of opportunities because you'll have a lot of data related to this particular disease because it's a common one. So you'll have tons of opportunities to learn the representation vector of this particular common disease. In that case, maybe you could come up with a way to design a model so that at least when you're trying to represent this particular rare disease, you can pull some knowledge indirectly from this to here because it is connected by this parent, the benign neoplasm of colon. So maybe there's a way you can, like this part, like the knowledge accumulated in this particular code can be like propagated like here to here and here. So you don't have to start from ground zero when you're learning to represent this particular code. So so that is why it's important to use a reliable source of knowledge. If this whole structure was like a complete bogus, it was like completely random structure, that like this kind of knowledge transfer wouldn't work at all, because like this code and this code will have nothing to do with each other if this whole structure was randomized. So we'll see, yeah, we'll get to that in the later like experiment section. So you get the idea. So yeah, and maybe like if this parent is super rare, but this one is not, then maybe this node can borrow knowledge from here, or maybe this can also borrow knowledge from here. But I mean, the travel distance from this node to this node would be like longer than this node to this node, because it has to go like 1, 2, like 1, 2, 3 hops compared to like 2 hops here. But anyway, so at least you can like borrow knowledge from distant cousins as well. So that's the whole idea. Right. So any questions so far related to domain knowledge or the intuition behind why we use domain knowledge? Nope. All right. So the architecture of Graham model, it looks like this. So it's when you understand this, it's pretty like quite straightforward. So this knowledge tag is what we call the diagnosis hierarchy in this example. So in Graham, Graham itself is a very generalizable model, but particularly in the paper we use disease code hierarchy. So you can think of this as an IC9 code like system. So this will be the root, and then this will be like parent, like grandparent, or like one of the ancestors, and this is another ancestor, and then so the node with dotted circle, so the dotted circle is here, 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 like they are the ancestors that you don't see in the actual EHR. And the solid circles, like here, 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 they are they're the leaf nodes that you do see in the EHR code, EHR raw data. So typically this would be 5-digit IC9 codes, and this would be like 3-digit IC9 code, and like something like that. And the key assumption in Graham is that when you're trying to represent these leaf nodes, the 5-digit IC9 codes, you don't represent them. You don't learn the representation vectors of these leaf nodes independently. So that is what we did previously when you're trying to when you just naively apply RNN to your EHR. What you're doing is you're independently learning the representation vectors of all the leaf nodes like separately. But here in Graham, we're trying to rely on the domain knowledge, the disease code hierarchy, to learn the representation vectors of the diseases. So key assumption is that when you're trying to learn the embeddings of this, you don't do them independently, but you assume that the representation vector of the leaf node is actually a convex sum of the entire chain. So when you're trying to represent this, you pull knowledge from itself, but also from its parent, also its grandparent, also its great grandparent, and all the way to the top, all the way to the root node. So from the root to the bottom, we can see a chain of nodes. And what we propose in the paper is that we should take into account all the nodes in the entire chain to represent the leaf node. So you can assume that there should be embedding vectors for all the nodes in the knowledge stack in the disease code hierarchy. Not so in the previously there were only embedding vectors for the leaf nodes, but now we assume that there are embedding vectors for all the nodes in the DAG. Right. So like CA would have like EA, CC would have EC, CG would have EG, CI would have EI. So there would be like predefined embedding vector space. So, and as I said, when you want to represent the CI, the code CI, the leaf code, as a vector, you need to weight sum all the nodes in the chain. So it would be EA, the embedding vector of the code A. So EA times some weight plus EC times some weight, and then EG times some weight, and EI times some weight. And the weights should sum up to 1 because we want them to form a convex sum. That was the key idea. Right. So once you do that, you weight sum them. So you weight sum them. So it would be alpha ij ej. So alpha ej would be like the corresponding embedding vector for C. Oh, I'm sorry about that. Yeah. Right. So yeah, gi. So all right. So the final representation vector, or the final embedding vector of the leaf node ci would be gi here. So as I said, it's a convex sum of all the nodes in the chain. So this is where the convex sum occurs, and alpha weights should be the attention weights because they should sum up to 1. So so in order to use attention mechanism, then you need to have an attention generation function. Some function should generate the attention weights on the fly. So that would be a we don't have a okay. I forgot. I guess we don't cover that. Sorry about this. But so the way that you generate the attention function is just use a feed-forward neural network with a single hidden layer. So it's just a like multi-layer perceptron with one single hidden layer. It's a very simple architecture. So that would actually, let me draw that here very briefly. So there would be a function that that accepts a pair of embeddings, and then they would go up one like this, and then there will be a final scalar value. All right. So there is a separate NLP, feed-forward neural network function, that accepts a pair of embedding vectors. So it would accept like EI and EG, for example, EI and EG. So in this scenario, I'm trying to represent CI as a GI. And in order to do that, you need to calculate all the alpha weights here. So in this particular case, I'm trying to calculate alpha GI. So the attention weights coming from these two pair of nodes, CG and CI. So EI, EG, and then so you concatenate them, and then you push them through a nonlinear activation. So this would be some hidden layer, and then you push that again to the final scalar value, some scalar value that ranges from negative infinity to the plus infinity to the positive infinity. So you do that for all pairs. You do that for itself, CI and CI. So EI and EI, EI and EG, EI and EC, EI and EA. So all pairs in your entire chain to like calculate the compatibility between two nodes, and then you generate the scalar values, and then you take all those scalar values, put them through a softmax to get the final attention weights, the alpha weights. So this will be your attention function. Let's call this attention function, like, and then it would get 2 arguments here. All right. So that's how you generate the GI, which is the final embedding vector of CI. And you have that for all leaf nodes. Like CH would have GH, CK would have GK, like CD would have GD, CD would have GD. Like, so this embedding matrix here would have the would have the dimensionality of D here. So it would be maybe like 128 or 64, 256, depending on how you define it. But now the dimensionality, the number of columns would be the same as the number of leaf nodes. Like leaf nodes. Because we know this final embedding vector are used for representing only the leaf nodes. So the ancestors are no longer part of this embedding matrix G, right? So that's I hope that's pretty obvious. All right, so let's clear out everything. Yeah, okay, so as I said, you do this to weight something using the attention function for all the leaf nodes and then construct the embedding matrix G. And then that's when you use this to roll up. Sorry. This is, and you use this G embedding matrix to represent your visit vector. So if you remember previously, the visit vector was like a multi-hot vector. So there is a very highly sparse binary vector where you set the dimension that is active to 1 and all the others will be 0. Like, for example, like in your visit, if you had cough and fever, then only the cough and fever dimensions will be 1 and all the others will be 0, if you remember. So typically what we did to embed that into the RNN in the previous lecture was that you just take that multi-hot vector, multiply that multi-hot vector to some weight matrix, and then derive the visit representation vector V, and then push them into the RNN. That was what we did. But here now, instead of using WX here, we are using the G matrix, embedding matrix. So the only thing that we did on the surface is we just replaced the embedding matrix from W to G. But now G was constructed based on the disease code hierarchy. So it has domain knowledge embedded into it. It has domain knowledge injected into the embedding matrix. So that's the only difference. So you do that, and then you derive the VT, the visit representation of the teeth time step, and then you push that into your RNN or transformer or CNN, whatever you want. But the important thing is that we are now using the embedding matrix that is based on the domain knowledge, like correct domain knowledge. Right. Okay, so moving on to the experiments. So any questions so far with the architecture? All right, good. Finally, some question. So G is fixed, right? And also,
so our second question. So our input vector X does not contain only our IC9 code, right? So there's lots of other information like gender or other things.
I'm sorry.
So,
I'm sorry. I thought my AirPod was connected, so I couldn't listen to you in the beginning. Could you repeat your question again?
Okay. So my question is, so our input vertical vector does not. I think as far as I know, it does not contain only IC9 code, right? It contains a lot of other information like some other visit on gender and maternity. So for that case, we applied this G matrix only for the ICD9 code parts, and we assemble that again.
Yeah, exactly. You can do that. So in previous examples, we were using not only disease codes, but also like medication codes and procedure codes, and also gender and stuff. I guess, I mean, gender is it's only a binary information. You're either male or female. So there's not much domain knowledge to be injected into that space. But for example, let's say you're using 3 types of information: diagnosis, medication and procedure, and you only have domain knowledge, or you only have the code hierarchy for the disease codes and not for the medication and procedure codes. In that case, you can construct a G matrix for the diseases only, and then just use the medication procedure as we did before. So you just concatenate the G matrix with other embedding matrices used for medication procedure. But the effect of using domain knowledge in that case wouldn't be that big anyway, because it's more technical, but the knowledge that you lack from disease codes could be complemented by like medication codes and procedure codes. Like, for example, the reason that I don't really care much about demographic information when I'm actually doing like some project or some application, like for example, I hardly use gender information, for example. It's because if you use disease codes and medication codes, then they already kind of like provide all the information that you need that you can get from using gender information. For example, like some disease, or like male and female get different disease and get different medications. So if you use like a lot of disease information, if you use a lot of medication information, and on top of that, if you use like procedure informations, then you can kind of guess the gender of the patient already without actually seeing the gender information. So in that sense, when you start using a lot of information together, then using domain knowledge for a subset of information wouldn't be that much helpful. So in reality, like it's okay not to use domain knowledge, to be perfectly honest. If you just have a lot of information to begin with, like if you have like millions of patient records and a lot of features that make sense, then you don't really need to rely on domain knowledge. The philosophy or the essence of deep learning is that you don't want to care about domain knowledge. You don't really give a damn about like domain knowledge, and you don't want to like hand select features, and you don't want to do hand feature engineering and stuff. You just want to pour your data into a very big machine, into a very big model, and then you want to somehow magically see it work out. And that actually does work out if you have infinite amount of data. I mean, theoretically. So this domain knowledge is it's only for a specific use case where you don't have a lot of data, but you do have a lot of domain knowledge, which is not very, I guess in NLP and image, it's not very often that you encounter that like specific scenario, because in NLP you typically have tons of knowledge. Like you have like Wikipedia, Wall Street Journal, and all kinds of like free text lying around. But in EHR, in healthcare, data are very expensive, and there's like privacy issues. So maybe this kind of approach, using like combining domain knowledge with very small amount of data, could be helpful. So that's the whole spirit of this paper. But in reality, if you have a lot of knowledge, if you have a lot of data, you don't need to care about domain knowledge. All right, and so did that answer your question correctly?
Okay, thank you. So in practical research, we have a domain knowledge about our diagnosis code and the medication. So we use them both, but not the other information such as gender that we don't have any domain knowledge, right?
Mm-hmm. Mm-hmm.
Okay,
correctly. Yeah. All right. So, and this first question is G fixed? So G is actually not fixed, because, as I said, each node in this knowledge deck, or the disease code hierarchy, has a corresponding embedding vectors, E's, and they are trainable. So G actually is just a weighted sum of the E's. So when you're training G, you're actually training E's, the embedding vectors of all the nodes in the knowledge nav. So if you can imagine, the parent codes, the parent nodes, like ancestor nodes, would be trained more often compared to leaf nodes. I hope that's very clear to all of you, because each individual G embeddings in the G matrix is a weighted sum of the all the chains. There's chain here, there's chain here, there's also chain here, there's chain here. So you can imagine that CC or EC, to be correctly, EC would be more, it would be trained more frequently compared to CG, and CG would be trained more frequently compared to CI. Is that clear? I hope that's clear. That's the whole like essence of this GRAM model architecture. We want the parents to be ancestors to be trained more frequently so that the leaf nodes can borrow knowledge from the parent nodes in case the leaf nodes are rare nodes. All right. Okay. Actually, we can see that happen when you analyze the attention behavior, actually, which is pretty interesting. All right, so moving on to the experiments. Any more questions? Okay, cool. All right. I like audience participation. What is AII for CI? How to get that value? So that's a good question. AII for CI is actually just a stupid way to calculate the self-affinity or self-compatibility. So before, when I was drawing the attention function, I was feeding in EG and EI to get the alpha GI, right? So in order to get alpha II, you just simply put EI and EI into the function. So it's a self-compatibility, and you would assume that the alpha II would be always the strongest because it's self-compatibility. But interestingly, no. Sometimes alpha GI is the strongest, and sometimes alpha CI is the strongest, depending on how rare the code CI is. Isn't that interesting? So is that the correct answer? How do we train the attention neural net? I mean, is there any target value for the attention? Good question. So attention function that generates the alphas will be trained end to end, because as I said, when you're training, let me remove my chat box. All right. So when you're training, for example, let's say you're doing mortality prediction or maybe heart failure prediction. Some signal will be coming from the top, from the predictive model, the Y. So you will be using like cross entropy function or mean squared error, some loss function. So from there, the error will back propagate to here, to here, to here, to the G, right? So it'll back propagate to the G. And as I said, when you're training G, you're actually training E's, but the E's are weighted, but the G's are not just the sum of E's, it's a weighted sum of E's. So the weights alpha are coming from the attention function. So so the signal will come both ways. So when the error back propagates and arrives at GI, it'll go both ways into E's and the alphas. And when I say the error goes to alphas, it's actually going to the attention function. So the attention function will have an indirect signal or the target value, which is to maximize or to minimize the cross entropy function of this final model. Does that make sense? All right, cool. Right. So yeah, that's typically how like attention functions are trained. Attention functions are just actually helper functions that try to maximize the performance of the model. So it doesn't usually have like a given target value. But interestingly, when you train your attention functions like that, I'm talking about in a general sense, any attention functions that you use in either transformer or retain or a very old version of like translation models like English to French. Like attention functions are helper functions, but when you train your entire network and see how the attention function behaves, it behaves in a very like reasonable way, as you will see in, I don't know, slide number 30 or something in today's class. All right, so moving on to the experiments. We don't have a lot of time actually. All right, so moving on to the experiments. So it's the I used 3 different datasets to test GRAM. So 3 different datasets, 2 different prediction tasks. One is, of course, heart failure prediction using the 30,000 Sutter Health dataset. But I'm in this time also using Sutter PEMF and Mimic 3. So Sutter PEMF is actually the superset of Sutter HF cohort. So when I was building the heart failure training set, it was coming from the Sutter PEMF, the mother dataset. So it's a lot larger than this one. And Mimic 3, you know what Mimic 3 is. So two tasks. One is heart failure prediction, as you will already be familiar with. I just given like a longitudinal EHR, try to predict whether the patient will have heart failure or not in the future. The other is something called predicting next step diagnosis codes, which is pretty similar to language modeling in like NLP. Like in language modeling, you see the sequence of words and then try to predict the most likely word that comes after. Like, let's see. I like cats and something. Then that something. Trying to predict that something would be like language modeling. And of course, based on probability, it would be very likely to be dogs, not cars. Like cats and cars is weird, but cats and dogs is more likely, something like that. So we can do the same thing for EHR. So you see a sequence of visits and try to predict all the things that would happen to the patient in the next visit. So you predict like the disease codes that would come after the current time step. So it would be like generalization of language modeling. And I did that for using these two datasets, Sutter PEMF and Mimic 3. And for the medical ontology, the disease code hierarchy, I didn't use ICD-9. I used something called CCS multi-level diagnosis hierarchy. But the essence is the same. It's just some tree-structured disease codes. All right. Okay, so the models are Gram. So I'm comparing a bunch of different models. Gram is the one that I'm proposing. Gram Plus is something a bit more advanced than Gram. So in Gram, there were a lot of like embedding vectors, E vectors for all the nodes in the DAG. But so when you're training them, you typically initialize them randomly, like using some random value, like maybe draw from Gaussian distribution or whatever. But you can actually pre-train them using word2vec or glove type of thing. Like you can pre-train them using unsupervised embedding learner. I think I use glove, but you can also use word2vec to train these E's. And the way that you can train them is, as I've shown you guys in the previous lecture, you can like directly apply word2vec in the longitudinal EHR. So Gram Plus is the one that pre-trains those E vectors. Random DEG is the one that you should focus on. Random DEG is where you shuffle the relationship between parents and children in the disease code hierarchy. So this represents a wrong domain knowledge. These represents correct domain knowledge. And RNN and RN plus are just plain without the G matrix. We just embed the code, disease code using the W matrix. And RNN plus is where you pre-train the W matrix using glove. Simple rollup is a stupid way to inject domain knowledge, which is to just convert all the leaf nodes into like great grandparent, something very up in the hierarchy. So that's why the number of codes drastically decreased from like 10,000 different ICD-9 codes to only 300 300 diagnosis codes, because you're mapping all the leaf nodes into a very like higher up ancestor node. Rollup rare is a bit more clever. So you count the number of occurrences of the leaf nodes in your training code, training data, and select only the rare ones and then convert them to like the ancestors. So you leave out the popular ones, the common ones, and then you only convert the rare ones to the like higher ancestor node. So that's why it's a bit like a lot larger than 283. So it's like this is like the middle ground of this and this. Right. So these are the comparison models. And starting from the heart failure data set. So what I did in this experiment is we changed the size of the training data. So we fixed the size of the test data, but we changed the size of the training data using only 10%, 20%, 30%, all the way to 100%. So in this case, in this experiment, Gram Plus and Gram always outperforms other models. So, and in some cases, in like lower volume area, like 30%, the gap between Graham and the other baseline models are wider compared to like, I don't know, like 90%, 10%. Like 90%, this is 8447 and this is 8345. So it's not that big of a difference, but in 30%, like it's 8340 and 8162. So it's a bit more, the gap is a bit wider. Interesting thing is here, random DAG always performs the worst in all percentages. Like it's always worse here, worse here, worse here. Like it's always the worst. So the obvious lesson is incorrect domain knowledge doesn't help. It not only not helps, but it actually hurts your performance. So you can actually see that Graham architecture is trying to use domain knowledge, and if it's the correct domain knowledge, it'll increase your performance. If it's the wrong domain knowledge, it'll hurt your performance. So it's a pretty clear message. Moving on to the next prediction test, which is the next step diagnosis prediction on two different data sets. One is the superset of Sutter, another is Mimic 3. And so these buckets, like 1 to 20, 20 to 40, 40 to 60, they represent the rarity of the diagnosis codes. So it's like different percentiles of different bunch of different diagnosis codes. So the diagnosis codes in this column are the most frequent ones. Diagnosis codes in this column, 1 to 20 bucket, is the rarest ones. And you can see for the rare codes, Gram Plus outperforms all the other models, but when it comes to more frequent ones, not so much, unfortunately. It RNN Plus or random simple rollup seems to do pretty well in both cases, in both Stutter PAMP and Mimic 3. So unfortunately, the reason that happens is, first of all, the attention function is probably not powerful enough. So which means that these are pretty frequent codes. So you should do, when you're relying on domain knowledge, you should at least do as good as well as other models that don't rely on domain knowledge, but it does not. So obviously this is because your attention function is not generating the attention weights properly enough so that it is like the Gram Plus is underperforming. So if you're, as I said, we were using only like a feed-forward neural network with a single hidden layer to generate the attention weights. But if we could maybe use a more advanced model, a more powerful model, maybe then we could see like better performance from Gram Plus or Gram. And another caveat is the output space of these both tasks, the next step diagnosis prediction task, is only 283 because we use the rolled up version of the disease codes as the output space. The thing that we're trying to predict is not the 10,000 IC9 codes, it's the 283 rolled up codes. So there's a significant advantage to the simple roll up model because the input space and the output space are exactly the same. So it's not a very fair game to begin with, but still, some lessons could be learned here. All right, so now moving on to the visualization. This would be a bit more interesting compared to just seeing a bunch of numbers there. So, so before, these two tasks were to see if Gram could cope well with one of the challenges, which was data insufficiency. Now we're moving on to the interpretability aspect of the Gram, so visualization. So here, what we're seeing is that these are a bunch of, as I've shown you in the previous class, these are a bunch of different like code. Like every single dot here is a single diagnosis code, and the colors represent the most general diagnosis category in this knowledge DAG, the disease code hierarchy. So these colors are the categories that fall right beneath the root code. These codes are the most abstract general category. So like neoplasms and like infectious disease and such and such. So these are the representation, the diagnosis embeddings in the 2D planes learned from skipgram and glove. So note that I didn't use skipgram and glove in the prediction tasks. So I'm just like showing them for references. So you can see that seems that skipgram is a bit more structured. It's learning a bit more structured codes compared to glove, which is like almost like scattered randomly. But here you can see at least the gray codes are sticking together. And of course, like green codes together, like pink codes together, something like that. Now moving on. So RNN and RNN plus. Now you can see there are very small number of structures that you can see in the outside, but in the middle, it's all scattered around. And also it's the same for RNN plus, so it's very like unorganized. And now you move on to Gram plus. Now you can see a lot of structure here. It's like the code clusters are clearly cut from one another. So it's not only that. So not only that the colors don't overlap randomly, but the substructures are well preserved as well. So all the pink codes are what? Pink codes are injury and poisoning. But if you look at this, these are like all the diagnosis codes in this like cluster are related to fracture of lower limb, and all the diagnosis codes here are related to fracture of upper limb. So these labels are the intermediate categories. The colors are the highest categories. The labels are the intermediate categories, and of course the dot itself, the circles itself are the lowest, like the leaf nodes in the hierarchy. So you can see it's not only that the highest category is preserved, it's the intermediate categories are also well preserved. So this whole diagnosis structure is reflected in this embedding space. Right. All right, so question. Do you try similar embedding visualization with UMAP instead of TSNE? Unfortunately, I don't know what UMAP is. Maybe you can explain to me what UMAP is, Michael? I'm not sure if you're speaking or typing. All right. So anyway, I'm guessing it's one of the other ways to like reduce the dimensionality. But I'm pretty sure. So I don't know about UMAP, but oh, right. Let me just quickly see that. Uniform manifold approximation and projection of dimension. Oh, okay, I see. I guess you would probably see a similar like structure if you use UMAP as well. As far as I know, TSNE tries to when TSNE reduces the dimensionality from like 128 dimensions to 2 dimensions, like in this case, it tries to preserve the distance between all the like pair of codes, pair of embeddings. I guess uniform manifold approximation is maybe has like similar motivation. And I'm quite sure that if you use PCA to downsize the dimensionality, you will see similar like visualization as this. All right, so moving on to, so this was Gram plus. Gram without the pre-training of the E embeddings, you'll see similar structure. So like very well clear-cut clusters in the embedding space. All right, another question. As far as I remember, T-string preserves local structure more at standard perplexity. Even tries to. Oh, I see. Okay, so local structure versus global structure. In that case, then I'm pretty sure we would see even more high, like better visualization. So as you said, T-string only concerns, well, not only, but mostly puts a lot of weight on the global. I mean, the local structure. So local structure meaning that these pink ones are like clustered well together, but the distance between the pink cluster here and the pink like orange cluster here, they don't really mean a lot of things. It's just that they're far, they're they're far away apart. But just because like the orange ones are far away from here compared to the green ones far away from here doesn't really guarantee that the orange ones are more like similar to the pink ones compared to the green ones. Doesn't guarantee that. So, but if you use UMAP, maybe we could learn, maybe that kind of information would be also preserved in the lower dimensional space. All right, so moving on. So Gram, as I said, so Gram also well preserves the structure. Interestingly, random deck does not. So you can see some clusters, some like hint of clusters here, but mostly it's all like very unorganized in a lot of the area. And this all again, shows the why you should not use incorrect domain knowledge. Because if you use the incorrect domain knowledge, then there's no reason why the model should learn the correct representation of the embeddings. So like there's a very clear comparison between gram and random DAG. That's a very clear message there. All right, so moving on to the attention behavior analysis. As I said, so you will see some interesting insights here. So the assumption from the core assumption of gram was that when you are trying to inject the domain knowledge, we were hoping that the rare nodes would be indirectly learning from the popular, the frequent ones, frequent nodes. And here we're trying to see that happen here. So we've picked 4 different disease codes: other pneumothorax, essential hypertension, joint disorder, the last disease code, need vaccine for flu. So technically, the last one here, this is not a disease code, but as I said, ICD-9 codes are for billing purposes. So maybe the doctor gave vaccine to the patient and charged the reimbursement form with need vaccine for flu. I think this is like some weird ICD-9 codes, like something that starts with V or something that starts with E. Anyway, so 4 disease codes, and we've laid them out in 2 different axes. One is it rare or is it frequent? And another axis is, does it have a lot of siblings or does it have few siblings? So siblings would be like this would be a sibling of this. This is a so they are siblings basically. Like having the same parent would qualify as a siblings. So all right. So yeah. So one axis, is it rare or is it frequent? The another axis is, does it have a lot of siblings or does it have a small number of siblings? All right. So moving on to the attention. Okay. So 4 diseases, and these nodes represent the chain. So the leaf node represents the disease itself, and the size of the node represents the attention that it is receiving from the model. So, and also the bar graph it's the same thing. Like the larger the node, the stronger the attention. And here the 5 sib means it has 5 siblings. So, and yeah, it's 5 siblings. And this number in the parenthesis represents the number of occurrences in the training set. So other pneumothorax has a very small number of siblings. It has only 5 siblings, and it is a very low frequency node. You only see in the entire training set, you only see 1 occurrence of other pneumothorax. So sibling low, frequency low, and in that case, there's like if this is a rare code and it doesn't have sibling, then the only way you can represent this is by pulling a lot of knowledge from one of these ancestors, like here. So a lot of attention is pouring towards the top ancestor here, because it has such a poor exposure to in the training set, and also not a lot of siblings, so not a lot of chances for the parent node to accumulate knowledge. So that is one pattern. Another pattern is number of siblings high, but the frequency low. So in this case, joint or disc disorder, only 2 occurrences in the training set, but gigantic number of siblings, 139 siblings of joint disorder. So you can assume that a lot of knowledge would be accumulated in the parent node, because as I said, compared to the leaf node, the parent node will be more frequently updated, and of course this parent will be a lot more frequently updated, so on and so forth. But of course, this compared to this node will have more fine-grained knowledge, because this is more abstract compared to this, and it has accumulated knowledge from 139 different siblings. So you can see a lot of rich knowledge would be contained within this node. So that is why the attention is pouring towards focusing towards this particular node. So it's good to have a lot of siblings, you can see. Third pattern, not a lot of siblings, but a lot of frequency, high frequency. So essential hypertension, gigantic number of 40,000 exposures in the training set, but only 2 siblings. So you can see it should be pretty self-sufficient. 40,000 number of exposures is a lot of numbers. So you can see a lot of knowledge is just being pulled from itself. So attention is just focusing on itself compared to like its ancestors. And the last pattern is a lot of siblings, a lot of exposure. So need vaccine for flu has 9,000 exposures in the training set, and it does come with a lot of siblings. So you can see a bit of like a balancing off is happening here. It does borrow. It does collect pour a lot of attention to itself, but it also pours some attention to its parents because it has a lot of siblings. So some good knowledge would be accumulated in the parent node as well. So it's a bit more like distributed compared to like this here, the focus distribution here. So yeah, so the attention behavior analysis shows that at least it is the Graham model is at least like showing the behavior that we intended we intended intended for it to show. So aligns well with the assumption. All right, so the conclusion is leveraging domain knowledge improves performance across data systems. So across data sets mean like it's empirically we've shown that it improves performance in three different data sets and 2 different prediction tasks. And of course, that's only when you use the correct domain knowledge. If you use incorrect domain knowledge, it'll never fly. And healthcare is abundant with domain knowledge. So it's not only for disease codes, but for like procedure codes, there's CPT code hierarchy. For disease codes, there's NDC code that we just talked about. And then, of course, there's something called drug network, which is like very often used when people try to predict the adverse drug event. So adverse drug event is when you take 2 medications at the time, and then there's like unforeseen side effects because 2 medications like interact with each other in your body system. So, and you want to prevent that from happening. So you want to predict whether that would happen if you take 2 medications at the same time. And you can't do that without any single domain knowledge. So people use drug network for that purposes. And again, like lastly, SNOMED ontology is a very comprehensive ontology. So if there's a way to like leverage that rich knowledge, it would certainly help us get through some challenges. Of course, and there's like other types of domain knowledge as well. So there's a lot of opportunities in this aspect. All right, so the original intention was to go through MIME and GCT, which is trying to view EHR as a knowledge source itself, but I guess we'll have to push that to this Thursday. All right, so any questions so far? Any question related to any material that I talked about today?